You ready?
Fantastic. All right, here's Joyee.
Joyee.
Hi, I'm Joyee, and today I'm going to talk about JavaScript and C++ in Node Core and how do they talk to each other. As you may have heard before, Node is implemented in both C++ and JavaScript. So one of the frequently asked questions from new contributors and users debugging into Node Core is, how do they interact with each other? In this talk, I will try to answer these questions by giving a brief overview of the layers in Node, how the code on different layers invoke each other, and how the cross-layer memory references are managed. I will show some simplified snippets from the codebase along the way and talk about some of the ongoing work in Node Core to improve the C++ and JavaScript interactions. If you're interested in hacking on Node Core, for example, if you participated in the first contribution to Node Core workshop yesterday, hopefully this can save you time in figuring out how things work. So if you're already familiar with how to build C++ add-ons, the C++ part of this talk probably would be fairly straightforward to you. If you are new to C++, no worries. The syntax is similar enough to JavaScript, so you could just look at the method and variable names and grasp the concepts. And a bit of introduction of myself. I work on the Igalia and Bloomberg collaboration, and I have been a member of the Node Technical Steering Committee as well as a V8 committer for a few years now. Recently, I've been working on improvements to the memory infrastructure in Node Core, as well as the startup snapshot integration and improvements to code caching. So now enough about me. Let's move on. A brief overview about the layers in Node. Most public JavaScript APIs in Node, like FSOpen, are implemented with a layer of internal JavaScript. In the source code of Node, this is mostly under the lib folder, which currently contains about 89,000 lines of code. The JavaScript layer usually validates the arguments and normalizes them a bit before going to the native layer. In the native, or like mostly C++ layer, which is under the source folder, there are currently 102,000 lines of code. They usually convert values between JavaScript and C++ and take care of things like permission, tracing, and hooks, and if necessary, they invoke the dependencies or system calls. And in between the two, there's the V8 JavaScript virtual machine, which actually is the biggest piece of code in the code base. Finally, there are obviously some third-party libraries that Node depends on, like libuv, OpenSSL, and zlib. And that's an overview of the layers. Now, let's look at some code examples. And a warning here, the internal property names shown here are just for demonstration purposes. They can be renamed in future, so please do not rely on them in the user land. And some names using examples are invented pseudonyms just to help you understand how things work. Now let's take a simplified version of the fs OpenSync method as an example to see how the JavaScript layer interact with the C++ layer. As you can see here, in the implementation of the fs module, we usually first get a binding object here, returned from a top-level internal binding call. This is an internal version of the process binding method. The process binding method is doc deprecated. Please don't use it in the user land. This is internal only now, okay? This object is used to organize the functionalities that the C++ layer exposes to the JavaScript layer. And this is how they are organized conceptually. So in each node instance, for example, the one on the main thread, there is one structure called environment. And in each environment, there is at least one JavaScript round. For now, there's usually just the principal round, but when the TC39 shadow round proposal goes through, there will be multiple rounds, each one of them for each shadow round. Now, each round here also contains a list of bindings. These are organized as keyed objects. So for example, there's one for FS, and there's also one for timers, and so on. And the JavaScript land can retrieve these objects using the internal binding call. And in that particular FS binding, there are yet a bunch of keyed properties. For example, the native open function that can be invoked from the JavaScript land that we saw before. Now, normally when we create the binding objects, what typically happens is that we create the object template for the binding object, which references many other function templates. And when we instantiate an actual object for this from this template, when internal binding is called, with any of the functions of this binding object, for example, open, gets called in the JavaScript land, VA looks up the C++ function following the pointers here. It sets up some internal states, for example, putting the arguments together into a C++ structure, and then it will just invoke the C++ function. So let's get back to the example. So in OpenSync, we first do a bit of validation of the arguments. We normalize them, for example, turning strings into numbers and assigning default values. And then we get the open function from the binding object, and we invoke it. And we go into the C++ land, which is a VA binding called open. And yes, Node still use raw VA stuff internally today instead of using anything fancy like the Node API thing that Michael mentioned before. And the C++ layer then converts the JavaScript arguments into C++ values, and then open the file with the libuv uvfs open method. This is the synchronous variant. And then libuv invoke appropriate system calls for the platform, and then return the result back to the C++ layer synchronously, because this is the synchronous variant. And then the binding converts the result into a JavaScript integer if it's successful, and then return it to the JavaScript land. So that is basically how synchronous bindings in Node are implemented so far. But is there a better way to do this? Is there a way to make them faster? Well, the answer is yes. So there is a new VA feature called fast API calls that can help us speed up the invocation from JavaScript to C++. So take this method, for example, which Node internally uses to guess the type of a file descriptor, and then return a constant that the JavaScript land understands as the type of the file descriptor. Now, to add support for fast API calls, we add another implementation here called fast guess handle type. So in the fast version, there's no need to worry about the arguments or like converting the return values. VA will do that for us. Now, similar to the FS open function we looked at before, this function is stored in a binding called util, and in function templates of that, we give VA two native functions, the original one and the fast one. When this function is run many, many times in the JavaScript land, and the argument and the return type is always matching the fast version that we have here, the next time VA calls the function, instead of calling the original version of the binding, VA would inline the conversions for us and call the fast version. Now, there are some rules about the fast API implementation. We cannot allocate JavaScript object here, we cannot call back to JavaScript, and we cannot throw exceptions. So many restrictions. In return, the overhead of calling from JavaScript to C++ is smaller because V8 no longer needs to set things up for those stuff. So it's about 10% faster for most bindings in Node. In some features, the call from JavaScript to C++ can be quite frequent, so they add up. And we're now adding support for fast API calls in more bindings internally in Node, as long as they can work with the limitations mentioned before. So that was the synchronous APIs, which normally involves just calls from JavaScript to C++. Now let's look at how asynchronous API works, and this usually involves calling back to JavaScript from C++. Here we have the fsopen method, which is asynchronous. The routines are very similar to that of the synchronous version, just that in the JavaScript land, Node creates an additional object to hold on to the user-provided callback. And in the C++ land, instead of invoking the synchronous version of the libuv method, we invoke the asynchronous one and pose a task into the libuv event loop with a callback. And when libuv invokes the native callback, we unwrap a bit to get back the JavaScript request object, and we read the incomplete callback that we assigned before in the JavaScript land. And then it converts the results back to JavaScript values and call back to JavaScript from C++. Well, that seems simple enough, except that this also, again, skips over an important detail. Actually, instead of calling to JavaScript directly, Node has an internal utility. If you have been building add-ons with asynchronous API before, you might be familiar with this. This is called make callback, and this wraps around a bunch of complexities for the actual routine in Node to call back into JavaScript. What does it do? Besides just invoking the JavaScript function, it also runs microtasks coming from the promises, if there are any, which is pretty common. And then it runs the callbacks killed by process nexttick, which is also fairly common. And if there are any async hooks configured, this needs to be emitted to the JavaScript land too. So theoretically, there would not be any overhead if there are no microtasks, no ticks, no hooks to run. But in practice, many of these get in the way in real-world applications. As a result, make callback tend to be much, much slower than simply calling back to JavaScript in V8, even though we have done some optimizations with it. But changing the actual behavior of this can break the ordering in which things get called. And order is sometimes assumed by users. So how the overhead can be reduced without hurting compatibility is still under investigation. So now we've talked about code invocations. Let's take a look at the memory. In Node, most JavaScript and C++ memory interfacing is done through wrappers that inherit from the base object class. Then we have many different subclasses of base object with different kind of life cycles. For example, one of the most important class is handle wrap, whose JavaScript wrappers are held live by C++ objects. And then the C++ objects are reference counted, usually to release the resources. In some libuv callback, libuv notifies Node.js that, for example, via UV close, that some resource is no longer needed. And then Node decrease the reference count of the C++ object. And when the reference count of the C++ thing is 0, Node then notifies V8 to release the JavaScript wrapper. the wrapper for TCP connections, TCP wrap, which we are going to look into later, it belongs to this class. And there's also another class of objects like file handle, whose memory management depends on the V8 garbage collector. Usually when the JavaScript wrapper is no longer reachable from the JavaScript land, V8 notifies Node about this, and Node deletes that C++ object. And finally, there are some special ones like binding data that holds on to all the JavaScript binding methods that we talked about earlier. Like that's the wrapper for whatever that gets returned from internal binding. This is usually gone, like only gone when the round is going away. For example, in the principal round of the main instance, that goes away when the node instance is actually shutting down. Okay, so now let's take a closer look at an example, the TCP wrap. Here are some code snippets simplified from the net socket class. This was created before ES6 classes became a thing, and for compatibility reasons, that's still not a ES6 class. That's why you're seeing all these prototype methods here. So when the socket starts a TCP connection via the connect method, the TCP new binding is invoked to create a C++ TCP wrap object. It wraps around this JavaScript object being constructed by VA. And then VA returns this object to JavaScript land. And in the JavaScript land, the socket puts it behind a symbol property called, handle. The C++ object here actually holds another strong reference to the JavaScript land TCP object, and that's what really keeps the TCP object alive. If for some reason the socket goes away by itself, the TCP handle would still be kept alive by the TCP, by the C++ TCP wrap as long as that one is still alive. But that don't usually happen if you just use the API normally. Then at some point in time, after the caller is done using this socket, for example, when the connection ends, typically the destroy method should be called on the socket object, which in turn invokes a close method that the TCP wrap inherits from handle wrap. And then the close method invokes UV close to close it asynchronously, and store the JavaScript land callback in TCP handle as a symbol property for invocation later. And then finally, when the VUE finishes closing everything, the onClose native callback is invoked, and that detach the TCP wrap from the C++ heap. So when the reference count of that reaches 0 in C++, the TCP wrap would be destroyed. And when the C++ object is gone, the strong reference to the JavaScript land thing is also gone, so that only references from the JavaScript land will keep the handle alive. Now, one last thing before we are done with the TCP wrap, we invoke the onClose JavaScript method, the JavaScript callback using make callback, and in this case, in the specific implementation of the socket, the close event will be emitted, and another bunch of cleanup will be done. And after close, everything will be gone when the socket and the TCP handle becomes unreachable from JavaScript. And here is what the corresponding heap snapshot will look like. So one quick note, when you see nodes prefixed with the node slash prefix, these correspond to C++ objects from node. And this is the relevant path of our previous example. The socket object references a TCP handle via a symbol called khandle. And then the TCP handle has a JavaScript to native reference to a node TCP wrap object. which it references back via another native to JavaScript edge. And the memory layout roughly looks like this. The public socket object has a symbol property storing the JavaScript TCP wrapper, and its wrapper is the JavaScript part of the TCP wrap class. It has an array of embedded data which contains a slot that's actually an pointer to the CPUB's TCP object. The socket, the wrapper, and the embedded data array, they all live in the V8 heap, whereas the TCP wrap class live in the node heap. In a heap snapshot containing a socket, you can see the references being marked as JavaScript to native and native to JavaScript here. This is a cycle, and that's why the DevTools shows the native to JavaScript edge as gray. That's what it does for cycles. And when the TCP wrap is detached, the TCP wrapper becomes fully managed by the V8 heap. And when there are JavaScript references, when the JavaScript references to it are gone, it will also be available to be garbage collected. So as we mentioned before, some objects in Node are kept alive by the JavaScript LAN instead. So for example, file handle, which is wrapped around by the objects returned by fs promise open. This references the JavaScript wrapper using a weak handle, so the CPUB's object does not actually hold the JavaScript object alive. It's the other way around. And here is a small snippet taken from the codebase. In the weak callback, that node passed to V8, which is supposed to be called when JavaScript object goes away, we delete the CPUB's object. The CPUB's object, and in the heap snapshots, the CPUB's objects are held alive only by JavaScript objects and have no other references from CPUB's. So these are prefixed with detached in the heap snapshot. So if you see them, that's what it means. And in the current setup, things work most of the time, but it's still a bit tricky. Many base objects have additional JavaScript references. Some of them are not. Some of them are also managed using the weak callback, which is actually a hack. As the V8 header shows here, the comments says that V8 does not actually guarantee when or if the callback is called. So far, the weak callback is usually called in time, and we don't usually rely on the callback for actual critical resource management. Instead, we rely on something like the close method that you've seen before. But still, this is not quite following what the documentation suggests, and wrappers can still be leaked if they're managed using this callback. And the incorrect usage of the weak references gave us the bugs like this, which is why, for example, a lot of JS users are still stuck at Node 16. So in case you're also stuck because of these, the bugs are fixed in 21 now. So please try 21 and see if they go away for you. And these fixes will be backported to older LTS releases soon. Now, instead of chasing all these incorrectly configured callback down to fix all these bugs, we have a different plan here to deal with these issues. We have a plan to improve the cross-layer memory management using the Oilpan library from V8. This is a library developed in Blink, the rendering engine of the Chromium browser, deal with similar issues. Later, this library got carved out of Blink and moved into V8 for other embedders like Node to use. So it's a trace-based CPUB's garbage collector that allows embedders to allocate their CPUB's objects in a heap that can be visible to V8. And with that, it's easier to avoid memory issues caused by cross-layer memory management, like the bugs that we've seen before. And this also allows us to migrate away from the hack the set weak callback hack that I've seen before that was advised against in the V8 header. This is recently bootstrapped in Node, and we're experimenting with some internal objects to migrate away from the existing model and to this new model. So that's all. Thanks for listening to me.
Okay, I think we definitely have a time for a few questions if anybody has some.
Okay. It's great to hear about this Oilpan CPP GC migration. I heard that you're helping to implement that. What would help you make progress there from the rest of the Node.js community?
I think so far the plan is to start from one of those more trivial objects, just in case, because we also have this ref counting mechanism that you kind of like, during the migration, you need to make the two work together before we've done all that. So there might be some kind of like crash that happen. So if you are on older versions of if you're on like older version of Node, you can like try them out on the newer versions of Node and see if it crashes you, I guess. And we'll try to provide some kind of mechanism for you to like fall back to the old memory management scheme. But we don't expect this to be like, just painless migration. There might be some bugs, and it will be helpful to get some feedback and try to make things managed better along the way.
Joyee, amazing talk. Joyee for president of Node. And so I have a couple quick questions. One is, like out of all the Node APIs, I'm curious which of the APIs you think is like kind of prime for more performance improvements, like the one that you just highlighted. And second question is like, is there a way to leverage WASM to kind of make things go faster? Because I keep hearing about all these crazy hacks where people just like wrap something in WASM and somehow it's just like faster. So I'm just curious if you have thoughts on that.
So in terms of what can be made faster, one thing that I recently noticed, but haven't done anything about it, someone else is doing something about it, is not technically an API, it's the ESM loader. Because Node Core is trying to make the ESM loader more of a thing, make ESM like more supported to the user end. And the ESM loader is not quite fast. And there are a lot of things that can be improved. For example, moving more things to the CPUBs land. I think that's one thing that's like pretty important for most users of Node, and it can use a lot of like optimizations and improvements there. And the second question is about using WASM internally in Node. We do have like usage of WASM in case you didn't notice. For example, we have something that detects the named exports in the ESM modules. And that thing is implemented in WASM, or implementing C, and then compiled to WASM, and Node run it as a WASM module. But I think that's a pretty specific case where like you have this pretty good library that you can use, and you don't want to like create a bunch of glue to do that, to import that in Node, so you just want it to WASM. Most of the time, it's still faster to just go bearable. I think that's also one of the reasons why we are not even using Node API or anything in Core. We just use the raw V8 stuff. Sometimes because as you've seen in Michael's talk before, the Node API does not target all use cases. They target like 80% of the use cases. And Node kind of like Node Core kind of falls into like the category where like it just needs a bunch of stuff that only V8 has for optimizations, for whatever. So even to this day, Node is still using raw V8 APIs for various reasons. I think it kind of also applies to WASM somehow. A lot of times, it just just do things simply and use very bare bones stuff. But there are definitely cases where WASM can be leveraged. For example, the HTTP parser that Pablo shared yesterday, implemented in Rust. There are some discussions about importing that as a WASM thing to deal with some of the build issues that we have. So sure, there are some plans, but to leverage WASM in Node, but probably not as optimization, but more like to get around with certain build constraints.
Hi, great talk. And I've seen a few talks and workshops about seeing like behind the curtain of Node, the C++, and it's great to see. But I'm just wondering about how there's like a push from like the NSA in America and OpenSSF's 10-point mobility plan to push organizations away from memory unsafe languages like C and C++. And I'm just wondering if there is a sort of, and I've seen a few talks about using Rust in Node Core, and is there a movement to use Rust or other memory-safe languages in Core itself?
Sorry. So, for example, Milo, the Rust HTTP parser is like one of them, but I think so far it's kind of difficult to migrate Node away from C++. One of the main reasons is that V8 is implemented in C++, so sometimes it's just easier if you want to be lazy. It's just easier to interface with V8 in C++. Even though, for example, there are also obviously runtimes out there like Deno that interface V8 with Rust. They have some kind of like binding wrapper for V8 APIs. But I think for Node, so far it's probably difficult to like yank the whole thing out and replace things with Rust. There are definitely like components that are more self-contained that you can implement in Rust and somehow make that interface with other parts of the code base. And I think that's possible. But in terms of the entire code base, I think as far as I can see, it's probably going to stay in C++ for most of the time. But for some components, definitely that's possible.
Okay. Well, thank you, Joyee. That was a fantastic talk. I love seeing the C++ stuff.